binomial probability distribution. This one is a little bit hard, so let's try to put our thinking caps on and let's understand how it works. So let's determine whether a probability experiment is a binomial experiment. And the binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are mutually exclusive disjoint outcomes. And we'll explain this why in a little bit. So these two outcomes are generally referred to as success, such as making a free throw, and failures. Experiments in which only two outcomes are possible are referred to as binomial experiments. This is slightly misleading, and I'll get to that in a second. But let's explain why it's a little bit misleading, actually. So let's take a die. In a die, there's 6 possibilities that are possible, 1 through 6. You can either get 1, 2, 3, 4, 5, and 6. Is it unfair to say that you can make this a binomial probability distribution? And no, the answer is you can make it a binomial probability distribution. And here's how. Simply put, we just assign basically like a Boolean truth or false value to it. And our true value is how many times we get 1. Or getting 1 and getting 6. Or, sorry, it's wrong. I mean, we could do that as well, I guess. But it's more a true or false value. So 1 or getting not 1. Or 1 or getting 6. These are two mutually disjoint outcomes because getting 1 does not affect 6. They do in the same trial, but not when running it again. So 1 and getting 6 can be made a binomial probability distribution even if there are more than 2 technical outcomes that are possible here. So let's go back to our binomial probability distribution. So let's talk about the binomial random variable. So as we know, random variable is the number of successes assigned to the outcome of a probability experiment. If we run a coin flipping experiment 10 times and we get head 6 times, that could be our random variable. And we mentioned that a little bit later. I love using the heads example for probability as well because it's so simple. But x is called the binomial random variable if it's the number of successes in n trials of a binomial experiment. Let's use this to introduce some notation. And we'll write this down here to make it a little bit harder to, or easier to understand. So x equals number of, I guess you could say successful trials. And we use successful very timidly because we can denote that someone getting cancer is a successful trial. Although it's not a good thing, that can be denoted as that. So even though it's successful, that doesn't mean it's altruistic or good in any extent. So it's important to note that. And we'll assign n as trials, as we know. So let's move on. 1 minus p is the complement, as we know, and the complement is simply, I guess you could just define it as 1 minus p. It's a little bit easier just to say that it's all the things that are not in your trial. So it's basically everything else but what you're looking for. So if you have a 20% chance of, or if you have a 1/6 chance of getting 1 on a die, then the complement will be 5/6, which is not getting 1. So let x denote the number of successes in n independent trials. So x must be between 0 and n. So that's some notation here. X should actually be capital right here, but it's fine. And here's my note there. And we'll get to this a little bit later. And I don't know why there's an O right here. But we can make a probability tree diagram and find out all the options. So let's say we flip a head once, or flip a coin once, and we get heads. Then both times we can flip a coin again, and we can either get heads or tails. And we'll do 3 trials, and we'll flip the coin again. So here we have HHH, here we have HHT, and here we have HTH, and here we have HTT. And note that here we'll use combinations because we don't care about the permutations. We'll assume HHT is the same as HTH, and that's simply because I guess it's a little bit easier to do that. Obviously, it's a lot harder to do it the other way. And we'll also get into binomial cumulative distributions, but we do it this way simply because we're trying to measure the number of successes or the number of possible times we get h. And note here, this looks much like a combination. If we flip a coin if we flip a coin 3 times, what is the possibility that we'll get heads 2 times? And we see here we get heads 2 times 2 out of the 4 times, which is a proportion, which then becomes 1/2. So this is actually probability because we're using equal probable approach or the classical method. So we'll go back to our notes here to quickly understand it. And here we mentioned how we can use the probability distribution as those who like sweet candy and those who don't. But there's actually a formula right here, and this is a little bit difficult to understand, so I'll get into it in the next pages. But it's really ingenious, so you should listen. Okay, well, we'll use this example, and we have 10 people. And A, B, C, D. So it goes up to J. Okay. So, let's assume that we want to pick 3 successes each time. So we'll interview these people. And we'll make a binomial probability distribution. So first, let's note whether they like candy or not. So we want to know if they like candy or not. So we'll write candy here. And what we want to know is if this person likes candy, if this person likes candy, and if this person likes candy, so on and so forth. And it's important to note that these are independent trials. Whether A likes candy has no bearing on whether B likes candy. Unless, like, A tells B to choose candy here in this scenario. But that's irrelevant here. So let's assume they're all independent trials. And let's say we want to see if 3 of them like candy, or how many possible times there is for 3 to like candy. So why is the formula 10 choose 3? And everyone knows the combination formula. If you don't, I made a video on it. But if we choose 10 choose 3, then these are all the possible different ways that these people can like candy. Or these are all the possible ways that there are 3 arrangements for them to like candy. So there could be A, B, C likes candy, A, B, C, A, C, D likes candy, A, B, D likes candy, so on and so forth. So as you know, this combination formula finds out the total number of people that like, or the total number of possibilities that someone can like 3 candy. What does this look like here? Let me just write this out. Or total number of ways that 3 people like candy, which I guess you could say is the same thing. That looks much like a tree diagram, which is simply all the ways, and we'll have like a huge tree diagram. Like this would be extremely big, but there will be 3 people that like candy here, 3 people like candy here. These are just simply 3 ways that you can, or these are all the ways that you can rearrange 3 people to like candy. But you might ask, like, what if 4 people like candy? Well, this is simply calculating, because our binomial probability distribution is going to be 3 people who like candy or nothing at all. So simply put, it's going to be the probability that 3 people like candy as our binomial random variable, and the other one is just going to be however many other people like candy, regardless of if it's 4 people that like candy, 5 people that like candy, 6 people that like candy. So simply put, these are simply 3 ways or possibilities that someone can like candy. So we have 3 here, we have 3 here, and we have 3 here, and so on and so forth. And these can be, as we mentioned, ABC, ABD, ACD, ACE, ACF, AFG, and so on and so forth. But these measure all the ways that people can be arranged into 3 groups. But now we go back to our multiplication formula or function. I guess it's formula. And since these are all independent variables, we can use the formula px, or actually, I think there is some other notation. I think it's r. Not too sure. Let's go back to what it was. It's a long thing. It's px and pn minus x. And why is it pn minus x? Where this top number is going to be 10, I believe. Well, it's important to note that the probability that someone likes candy, let's just say it's 0.5. That means for 3 people to like candy independently, it's going to be 0.5 to the third power, because we have to have the probability that one person likes candy, couple it with the probability another person likes candy and another person likes candy. I'm not too sure how this formula was found, but I think it was based off the conditional probability formula. But anyways, the probability to the power of how many people we want to have that probability, so 3 people liking candy, will give us the probability that 3 people like candy. But that's not it, because the probability that this is the probability that someone prefers candy at least 3 times, or that 3 people will prefer candy, or at least 3 people prefer candy. However, more people can prefer candy. So, this is simply this is simply insufficient to determine how many people will like candy. So we have to lock it in. And that we do this by n10 minus 3. So this is locking in the probability that the other 7 will not like candy. And if we group this together, we come here. And simply put, this whole part right here is the probability that 3 people will like candy. And the combination formula over here tells us how many possible ways it is to arrange all these groups into 3 people. If we do 4 people, then it's possible that or it's just insufficient, because now we don't know all the possibilities that the person can like through candy. But anyways, this is the probability that 3 people like candy, because we locked it in. The other 7 don't like candy based on this formula. So let's clean this up a little bit, actually. So let me just make it a little bit easier to read here. Then we'll do C and an X. So this part gives us the probability that someone likes candy. But what are we looking for? We're looking for all the probabilities combined. And the probability here is simply going to be, or the proportion that it gives us, is going to be 3 people like candy over total number of trials. And this gives us the amount of possibilities that there is that 3 people like candy. So simply put, it's how many ways we can rearrange 3 people, or we'll just do total possibilities. And since the possibility of each one is equal to that, we multiply that, because it's P, these 3 people like candy, or these 3 people like candy, or these 3 people like candy, and so on and so forth. So these are cumulative, and you add them up, which is the same as multiplying by the total number of possibilities times the people that like candy. So since we get from the combination function over here how many people like, or how many ways it is possible for 3 people to like candy, because they're going to fall into 3 of the 10, which we use this formula for. There's no other possible way. And since each one has this amount, so each individual, so ABC is equal probable to ACE, and is equal probable to ACD. And we're simply summing up all the possibilities here that they can be arranged into 3 people, and timesing it by how likely it is for each of these to like candy. So that's how the function was derived, or that's how it is defined. It's a little bit hard to understand. It's a little bit abstract. So let me just explain it one more time in quick detail. Px 1 minus px, or 1 minus pn minus x, times cnx. So let's go over here. Now px is the probability that, so if we assume it's 0.5 times people that like candy, and we want 3 people to like candy. As you know, the independence probability multiplication formula is just the product of the two. So the product of the two probabilities, or the product of the three probabilities, because it stacks. So we measure the first person and they like candy, then we measure the second person and we like candy, and they measure the third person and we like candy. So simply put, we're measuring all the different ways that the person likes candy. Or we're measuring the probability that 3 people like candy. However, this isn't sufficient, because this only guarantees that 3 people like candy. 4 people can also like candy. And all that does is make the sample space a little bit bigger, because we'll multiply it by another 0.5, which is 1 over 2. And so on and so forth. So it's a higher probability that 3 people will like candy than guaranteeing that 4 people will like candy, and more guaranteeing than 5 people like candy, and guaranteeing that 6 people like candy. So we lock in the other thing right here, 1 minus p n minus x, which tells us how many people don't like candy. So this guarantees that 3 people like candy and 7 people don't like candy. And the NCX formula calculates all the different ways it can be arranged into 3. So that means the total amount of outcomes that can yield 3 results. So the slot that fits in 3 only. If it was 4, then that wouldn't give us the total amount of probabilities that could fit 3 yeses or 3 successes. So NC minus x just gives us total probability. So we can rewrite this formula as probability, and we can assume it's probability since we use the classical method, times total possible outcomes. So it's just the tree diagram. And since we can rewrite this as, I guess since we're using the equal probable approach, the probability that 1 likes it, or the probability that, it would be 1 outcome, which is the person liking candy, over the total outcome times the total possible outcomes, since it's cumulative and you add them together. So since this is a probability that 1 outcome of 3 people liking candy, there's so many outcomes of 3 people liking candy, and since they're all cumulative, we can just add them up. And that's simply what I was trying to say. It's a little bit hard to understand. It's a little bit abstract, but that's what it is. So I explained this here. Let's say there's a group of 10 people. We want to use a random variable 3. We use 10 to choose 3, which gives total amounts of groups of 3 people that can be arranged. So basically, it calculates all the way that 3 people can like candy here. There can't be any other ways, because this calculates all the probabilities. And we multiply it by the independent chance that we choose 3 people from the group, and we multiply the 0.8 to the 7th to lock in that 7th people lose or don't fit into the random variable. Further conceptualization, all binomial theorems are choosing random variable like 3 wins out of 10. Then we are doing the probability of p this 3 wins or that 3 wins, which is why we multiply the combination, because it calculates all the probabilities that there are divided by total number of trials. And that will give us the classical method approach, assuming they're all equal probable. So simply put the formula as number of possible desired random variables, which you get from the combination formula, times the probability of getting the desired variables to the power of how many desired variables we want. This is simply just putting it into words what each variable means. And here's extreme simplification. Number of possible outcomes, or number of possible outcomes that they can be arranged into 3. And the number of possibility of each outcome, where the possibility of each where it measures the chance of success. And since each one has an equal chance of success, we just multiply together. So yeah, here's the derivation. It's a little bit complicated, but I already kind of explained it. The continuation is, since the probability of a win or the random desired variable occurring is desired variable slash total outcome. So then we use the number of possible ways of getting that within the sample size. It's just further on and further on. This is using technology. Notation P, x equals x. It's a little bit abstract. Standard deviation is square root NP times 1 minus b, which is, I don't know who it was derived by, but I think it was derived using variance. I'm not sure who it was. It's a little bit difficult. I don't know it at all, so I can't really say. And the mean of a binomial random variable is the number of trials, which is simply just the expected value here, actually. And I explain that here. And this is the final formulas. Binomial cumulative distribution is simply the same formula, actually, except we use sigma series notation, where we add together each binomial distribution and the chance that two people win. And so, like, if we want to know how many people, so like the example we used before from A to J, there's 10 people. And if we want to know the probability of 3 people or less winning, so I guess we'll do 2, 1, and since they're discrete, we can simply add them together. So it would simply be 10 choose 3, 0.5, since that's what we denoted earlier, 3.57, and we just add them up. So all it is just adding it up over and over, and it simply makes it easier for us on this calculator. I know I said I wasn't going to teach the technology method, but that's how it works. So that's it. And this is graphing binomial probability distribution, probability, and our discrete variables on the bottom. Note it's only for discrete, and we get into continuous variables later. So